Hello students, this is lecture number 20 of Signal and System course, and in today's lecture we are going to discuss about the Laplace transform methods used to determine the characteristic for LTI systems. And past couple of lectures we have discussed about how Fourier methods are very useful in determining the response of LTI systems. And today in today's lecture we'll be discussing about Laplace transforms. Before starting the lecture, I would like you to recall something from lecture number 12, and that lecture was about the response of LTI systems when complex sinusoids were given as an input. So if you remember, from that lecture we discussed about when a complex exponential such as e power st here is applied at the input of an LTI system, then the response of the system is also same complex exponential multiplied with some amplitude factor h of s, where s is a complex number. So h of s can be real and can also be a complex constant. It can be a real constant, it can be a complex constant. So the signal which has these kind of characteristics are called Eigen Functions of the LTI system. So Eigen Functions of the LTI systems are actually complex exponential, or in other words, exponentials. Complex exponentials are the Eigen Functions of the LTI system, and that is the main reason we try to represent all kind of input signal as a linear combination of complex exponential. This is what we did in Fourier series representation or the Fourier transform representation. Because if you are able to represent your input signal as a linear combination of complex exponentials, then you can compute the response of the system very easily. So the complex exponentials are called Eigen Functions of the system, and the value of h of s for particular value of s is called the eigenvalue. So I would like you to remember this for rest of the lecture. So move on. So again, from last couple of lectures in which we discussed about the continuous time Fourier series and continuous time Fourier transform, we realized how important continuous time Fourier series and continuous time Fourier transform are while studying the behavior of the LTI system, because CTFS and CTFT are used to represent any kind of signals as a linear combination of complex exponentials, and the complex exponentials are eigenfunctions of LTI system. So that is why they are very important tool in studying the LTI system. In continuous time Fourier transform, if you remember that the complex exponential were of the form e power j omega t. If you review the lecture number 18 and 19, you will see that the complex exponentials that we use were of the form e power j omega t, in comparison to e power st. So e power st is actually a general representation of complex exponential, and e power j omega t is the representation of a complex exponential when real part is 0, when s is only imaginary. So in Fourier analysis, Fourier transform analysis in particular, the s was equal to j omega. So it means the complex exponential had only imaginary part of the frequency. It doesn't had any real part of the frequency. So s basically here is a frequency, and s can be real, can be complex, and can be imaginary. So in case of Fourier transform, it is imaginary. So we can say that in Fourier transform we only consider those values of s which are imaginary, right? So when s is only imaginary, then only sinusoidal and cosinusoidal form of signals are present in the system, right? No other form can exist, right? And if you want to know why, you can again go back to the lecture in which I explained about the complex frequency concept and the complex exponential concept. I have explained this thing in detail. What happens when s is only imaginary, when s is real, and when s is complex, right? So what I want you to remember, that when we are talking about Fourier transform, then s is only imaginary, e power j omega t, and you can actually verify that by reviewing lecture number 18 and 19. So move on to the next slide, and we know that the eigen function property is also applicable for the values of s which are not only imaginary, right? So eigen functions, which is e power st, where s can be imaginary in case of Fourier analysis, or it can also have values which are not imaginary but which are real or which are complex, right? So Fourier transform is the study of the LTI systems when s is only imaginary, right? So but it is not the case always. S is sometimes complex, s is sometimes real, it sometimes is imaginary, right? So this observation actually leads us to a next step, which is generalization of Fourier transform, which is known as Laplace transform, right? So in other words, we can say that the Fourier transform is a special case of Laplace transform, right? So in Laplace transform, s can have any value. It can be real, it can be complex, it can be imaginary. And in Fourier transform, it is always imaginary, right? So in Laplace transform, when s is imaginary, Laplace transform becomes Fourier transform, right? So we can say that the Fourier transform is a special case of Laplace transform where s is imaginary. So in Fourier transform, eigenvalue e power st is imaginary, right? S is imaginary. And in Laplace transform, it can have any arbitrary value. This is the fundamental difference between the Fourier transform and the Laplace transform. So Laplace transform is the more generalization, right? So that is the reason why that when you study the transient behavior of the systems, or you study generally LTI systems, we use Laplace transform, right? In next semester, probably you are going to study the linear control system theory, in which you will see Laplace transform would be used throughout the syllabus in classical part for studying of LTI systems, right? And whenever you will study the frequency response of the system, then you will use Fourier transform, right, which is the special case of Laplace transform, because when we study the frequency response of the system, inputs are sinusoidal, and when we study time response of the system, not the frequency response, then we use Laplace transform, right? And the theory, the fundamental idea behind the use of Laplace and Fourier is that the Fourier is only applicable when s is j omega, when the signals are linear combination of sinusoidal waveforms, and Laplace s can have any arbitrary value, right? So it is to those functions as well which are combination of sinusoidal and exponential. So what is Laplace transform? You probably already know this because you have studied in mathematics, right? So just to go, quickly review this, the response of linear time invariant system having an impulse response h of t to a complex exponential of the form e power st is given by this equation, right? Y of t equal to h of s into e power st. We have already studied this in lecture number 12. So h of s here is basically Laplace transform of h of t, right, and it is given by this equation. H of s equal to integral of h of t e power minus st from minus infinity to infinity, right. So this is the definition of the Laplace transform of any time domain function. In this case it is h of t, which is the impulse response of any LTI system. Now here, if s is only imaginary, for example s is equal to j omega, then replacing s equal to j omega would give you the Fourier transform of h of t, right. And for any other value s equal to j omega, s equal to sigma plus j omega, this is a Laplace transform. So in general, the Laplace transform of a general signal, for example x of t, is defined as x of s equal to integral of x of t e power minus st dt. So the complex variables can be written as s equal to sigma plus j omega, with sigma as the real part and omega as imaginary part. Now let us solve this example to compare the Fourier and Laplace transforms. X of t is a signal which is given by e power minus at u of t, where a is greater than 0, so it is decaying exponential. In lecture 18 and 19 we have already found the Fourier transform of this signal, which is given by this equation 1 upon a plus j omega. Now let us find out the Laplace transform of this signal, right. So Laplace transform is given by this equation, where s is equal to sigma plus j omega. So let us substitute s as sigma plus j omega here as well as here, and also you can see that integral from minus infinity to infinity is now from 0 to infinity because of this unit step function. Now simplifying it further by separating the real and imaginary exponents, you can find out the Laplace transform of this function x of sigma plus j omega equal to 1 upon sigma plus a, which is the real part, plus j omega, which is the imaginary part. Or we know s is equal to sigma plus j omega, so we can write down the Laplace of this function as x of s equal to 1 upon s plus a. Now as I told you that we can use Laplace transform as a powerful tool for the characterization of LTI systems, right. So this is actually one of the most important application of Laplace transform, and as I told you, the classical control theory that we are going to study in the next semester is actually based on Laplace transform theory. So the Laplace transform of the input and output of an LTI system are related by this equation, right, which is also called the convolution, right. H of s and x of s are convoluted together to produce output y of s, right. This is also called the convolution property of Laplace transform, just like we had the convolution property of Fourier transform. So H of s, the Laplace transform of the impulse response, and x of s is the Laplace transform of the input signal. When they are algebraically multiplied together, in time domain it is basically convolution, and output is y of s, which is in time domain. So x of s here is input signal, y of s is the response, and h of s is the Laplace transform of the impulse response of the system. Now h of s is also called the transfer function of the LTI system, right, and it is defined as the ratio of Laplace transform of the output to the Laplace transform of the input, considering initial conditions of 0. Right. So transfer function actually helps you to determine the characteristics of the system. How we can determine the characteristics? By computing the roots of numerator and denominator polynomial, right. So roots of numerator polynomial are called zeros and are represented by symbol small circle. Similarly, the roots of denominator polynomial of the transfer function are called poles and are represented by small cross sign, right? So poles are the roots of denominator polynomial of the transfer function and represented by cross sign, and zeros are the roots of numerator polynomial and represented by small circle. Pole and zeros of the transfer function are plotted in S-plane to determine the stability of the system, and also you can determine other characteristics of the LTI system other than stability, right? So S-plane is basically a complex plane, right? Like other complex planes are. In complex plane, we have one axis which is real, which represents the real part, and a vertical axis which represents the imaginary part, right? And in complex plane, in S plane, we plot poles and zeros, poles with the cross sign. Here in this figure you can see we have two poles, one pole at -1, another pole at 2, right? Similarly, we have one zero which is located at 1. So in order to determine the characteristics of the system, of LTI system in particular, we plot poles and zeros of the transfer function in S-plane. And S-plane is basically a complex plane in which horizontal axis represents the real part of the S and the vertical axis represents the imaginary part of the S. In example 2, we are giving 4 transfer functions and we have to determine the calculate the poles and zeros of the transfer function in each case. So let us take the first one, in which h of s is equal to s minus 3 divided by s into s plus 2. So if you remember the definition, the poles of the system or the poles of the transfer function are roots of the denominator polynomial, and zeros are roots of numerator polynomial. So for zeros, find out the roots of numerator. So in this case, numerator is s minus 3, right? So what would be the root of s minus 3? S equal to 3, of course, right? So 0 is at 3. So system has only one 0 and it is located at 3 in S plane. Similarly, roots of denominator polynomial, there are two roots, right? One root at s equal to 0, another root s equal to minus 2. So we have two poles, one at origin of the S plane and another pole at s equal to minus 2. So this is how you can find out the roots of numerator and denominator, in other words, poles and zeros of the system. Similarly, in second case, we have only one 0, which is in fact at the origin of the S plane, right? And we have three poles, one pole at 1, another at minus 2, and third one at minus 3, right? And similarly, in other cases, you can find out the roots of numerator and denominator, in other words, poles and zeros of the system. Very simple, right? And from after computing the poles and zeros of the system, you can determine the stability of the system, right? So all the poles and zeros of the system are plotted in S plane to determine the stability. Now S plane is basically divided into two parts. One is the right half plane, which is on the right side of the vertical axis, imaginary axis, and another is the left half plane, LHP and RHP, right? LHP is the left half plane, which is on the left side of the imaginary axis, right? So if any of the poles lie in the right half plane, the system is said to be unstable, right? If system has, for example, 5 poles, 4 poles are in left half plane and 1 pole is in the right half plane, the system is said to be unstable, right? Why it is unstable, later on we are going to discuss about it. Similarly, if the pole lie on exactly on the imaginary axis, right, they are imaginary, then the system is said to be marginally stable. So when poles are imaginary, the system is marginally stable, and when poles are real or complex, then system is either stable or unstable depending upon where the poles lie, right? if they are real or they are complex and they lie in left of plane, the system is stable. If they are real or they are complex and they are in right of plane, the system is said to be unstable. So the stability only depends upon poles. It doesn't matter where zeros are, right? In fact, it does matter as far as the relative stability is concerned, but you know that is slightly beyond the scope of your course. So at the moment we are only going to discuss about the absolute stability of the system, which depends on the location of the poles in S-plane, and this is what we have discussed here so far. So moving on, now again we are giving 4 transfer functions and we have to draw the pole 0 map and we have to determine the stability of the system, right? So we know how to find out the poles and zeros. In this case we have only one 0 located at -3 and we have 2 poles at 0 and -2. Now we have to draw these poles in S-plane. So let us draw the poles and zeros in S-plane and determine the stability. Alright, so in part 1 of example number 3, we have transfer function h of s equal to s plus 3 and s into s plus 2, which is the denominator. Right. So the numerator, the roots of the numerator are zeros and it has only one root, which is at -3. Right. So you can see in pole 0 map we have one 0 at -3. Similarly, we have two poles, one at the origin of S-plane, which is represented by this, and another at -2. Right. So this is the pole 0 map of the system given by this transfer function. And as far as the stability is concerned, we can say that the system is marginally stable, right? Because we have one pole which is on the vertical axis, on the imaginary axis. So this system can be referred as the marginally stable system. And similarly, you can also plot the other three functions, pole 0 map of other three functions, and you can determine. Now we are going to discuss about why systems are stable when the poles are in the left of plane and are unstable when the poles are in the right of plane. So that is basically related to boundedness of the system. As you know, BO stability, that when a bounded input is applied to a system, then output is also bounded, then the system is said to be stable, otherwise not. So this is actually the same concept here. And what happens when the poles are in the left of plane, the response of the system is bounded when a bounded input is applied. And similarly, when the poles are in the right of plane, the system's response becomes unbounded even if a bounded input is applied, right? So to elaborate this, let us consider two systems, one which is stable by our definition and another unstable, right? So this one has one pole in the left of plane and another has same pole of the same magnitude but in the right of plane, right? So this one stable and this one now unstable. If we take the inverse Laplace in both cases, right, inverse Laplace of this would be e power minus 3t, a decaying exponential which is bounded, right, when a unit step input is applied. Similarly, the inverse Laplace of this 1 upon s minus 3 is increasing exponential when a unit step is applied as an input. So unit step is a bounded input. In this case, the output is also bounded, but in this case it is not bounded. So you can see when the poles are in the left of plane, the eigen functions of the system are decaying exponentials, and when the poles are in the right of plane, the solution of differential equation or solution of the transfer function includes increasing exponential which are unbounded, which makes system unbounded. So that is the reason that that is the reason of division in the left and right of plane of S domain, and that is actually related to the boundedness of the system. You can see in these figures, this one is bounded, which is decaying exponential, and this one is unbounded. So whenever one or more than one poles are in right of plane, the dynamic equation contains increasing exponential terms. The solution contains increasing exponential terms. So that makes the response of the system unbounded, and hence the overall system unstable. So that is the end of this lecture, and if you have any queries, you can contact me using the email address given in the first slide, and thank you very much for listening.